Welcome back, everyone. We'll now begin with the contributor talk session. I request Dr. Sukanya Mukherjee to kindly chair the session.
Thank you, Sharna. Good morning to all of you. I would like to call Swati Jain, and her topic of discussion is today on a study on role of distant neighbor over elementary cellular automata. Okay.
Good morning to everyone present here. I'm Swasti Jain and I have this opportunity to present the paper on a study on the role of distant neighbor over elementary cellular automata. Let's first start with the overview of what we're going to go through this presentation today. We are first going to go through the introduction, then the background, followed by integration of distant neighbor on evolution of ECAs, the methodology, followed by classification of ECAs based on robustness, results and analysis, conclusion and acknowledgement. So let's start with the introduction first. As all of you know here, elementary cellular automatas symbolize the simplest form of ECAs, where each cell in a lattice is in the form of three neighborhood two-state cell, which is affected by the neighbors on its left and right. In the early 1980s, Wolfram's seminal work has emphasized the potential of cellular automaton to comprehend the complexity and emergent behaviors in discrete systems, and has separated four types of Wolfram's classes, signifying class 1, class 2, class 3, and class 4. However, in our research, evolution of a CA involves local interaction between the immediate neighbors. So to signify this and take it more to the next step, we have tried to find what the role of a distant neighbor would be in the case of a CA. So the influence of distant neighbor interaction till now has not been fully explored in the case of cellular automaton. And the additional labor can be considered as an external influence that alters the behavior of a system. When we go forward, the resilience of a system to this external intruder under minimal conditions can be explored further. And we have studied the behavior of CAs considering that only one cell has a distant neighbor, that is one-way interaction between a cell that has been predefined and a cell at a distance delta. And it is observed that some ECAs are robust as a distant neighbor interaction has zero or minimal impact on its dynamics. Moving forward, we get to the background. And here the CAs are of one-dimensional, basically as we have defined it before, the CAs are of one-dimensional with three neighborhood, where the three neighborhood includes the cell itself and the neighborhood cells of right and left cell. Now, each cell is updated based on its current state and the states of its two neighborhood. Based on the Wolfram classification, we can say that there were four types of class rules. Class 1 is where all initial configurations converge to a fixed homogeneous state. Class 2 is the initial configuration converging to more than one fixed state, and separated periodic regions are produced here. Class 3 is such CAs produce chaotic patterns, and class 4 would be exhibiting behavior intermediate between periodic and chaotic. Such a CA would produce complex patterns. During this, what we have observed is that class 1, the information regarding the changes would eventually die out, and there would be no significant changes observed when integrated with the distant neighbor. In class 2, the changes remain localized, as in there might be perturbation in certain rules, but it's not something very significant that we have observed in class 2. In class 3, the changes propagate throughout the automaton, and in class 4, the information is carried by some localized structures. The integration of distant neighbor on evolution of ECAs. Now, there are some parameters that we need to define first and foremost, starting with the influence. So, the exhibition of class transitions is due to the introduction of long range interactions. So that was the first parameter that we defined when we wanted to study the distant neighbor. That is, if we are going to introduce an interaction with a distant neighbor, there might be some perturbations that we might find out and introduce basically in the long term. So with that, we have also observed that there might be some signs of criticality that might become visible in the long run. So now here, when we say signs of criticality, we mean in the context of CA that there is a complex balance between complexity and chaos. So with that, moving on to the periodic boundary conditions, to maintain the origin of the classical CAs, we have tried to implement the periodic boundary conditions here so that they implement and implicate how classical CAs would behave in the similar scenario. And each cell is updated based on the ECA rule except cell A. So cell is basically a central cell of this ECA defined here of any lattice size n, and there's a cell B which is going to be at a distance lambda from the cell A. Based on that distance, we are going to perform 6 logical operations between cell A and cell B that are from basically OR, AND, NOR, NAND, XOR, and XNOR. We did not take up the remaining two logical operations because using identity and zero operations would not help us further identify, because they would be repeating themselves in the cellular automata, and they would not help us identify any long range interactions between the cell A and cell B. The classes studied here are class 2, class 3, class 4 rules, and the class 1 rules have been excluded here due to the exhibition of minimal variability in the dynamics of the cells of the cellular automata. The methodology is as follows. So basically we wrote the code for this space-time diagram that would be generated before before the distant neighbors were introduced in the cellular automata and after the distant neighbor was introduced. So there were space-time diagrams, density plots, and heat maps. What we mean by density plots is that they would provide a range of the active cells present in the graph after the distant neighbor has been introduced. So that provided the density plots, and they provided the distribution of active cell density within the changed space-time diagram. And there is heat maps. So heat maps provided the difference between the initial space-time diagram and the changed space-time diagram. The lattice size ranged from small to large, where we took the small lattice size to be of 101 cells and the large lattice size to be of accommodating 1001 cells. And there were two kinds of initial configuration, where cell A was active, that is, cell A is the central cell that was active, and the remaining cells were set to zero. And there was the other initial configuration, which was arbitrary in nature, such that every cell present in that cellular automata had equal probability of being in state 0 as well as in state 1. The distance or lambda of cell A and cell B was taken to be in multiples of 5 and 2, so that we could check whether there were any critical appearances of patterns emerging when we ran them through different sizes of lambda. The time duration was initially set to 100, so we can observe any interruptions or any chaotic patterns appearing during the evolution of the CA for short term range. But if we did observe something appearing in any of the CA, we ran them for long term step evolution as well. Now comes the main point of the paper. So the classification of ECA is based on robustness. So we have defined a parameter where all the three classes, class 2, class 3, and class 4, can be identified and aggregated into separate 4 classes based on robustness. So what we mean by robustness here is could be identified as that a measure of the extent to which a rule's dynamics is perturbed. That is, in the space-time diagram, the distant neighbor alterations are that appear when the distant neighbor is introduced in the ECF. Based on the stability and resilience portrayed, the rules are further classified into 4 types of robustness categories, which are most robust, partially robust, weakly robust, and least robust. So what we mean by most robust is, let me first clarify this, that ECA-D means that ECA that has distant neighbor integrated into it. So that is the updated ECA. And that ECA-D shows high resilience under most robust category. That means that it will retain its structure despite the introduction of the of the distant neighbor in the cellular automata. And therefore, we have classified that as most robust. Some ECAs of this category displayed complete robustness. So complete robustness would be that under the heat map that we have introduced in the code, there would be no changes that would be identified between the original space-time diagram and the change space-time diagram. No heat map alteration in completely robust ECADs. Now, partially robust, under partially robust, ECAD exhibits moderate resilience and might have localized changes, but fundamental dynamics is preserved. So, if the changes might appear in any of the rules, they appear in particular patterns throughout the cellular automata and they are preserved in their own area without interrupting with any other area of the localized structure. The weakly robust, the ECAD differs significantly. Now, here potentially leading to transformation and dynamics. Now, there are certain perturbations that might appear in this, but they are not aggregate, like they are not altering the entire behavioral structure of the system. It provides more alterations or diffuses the entire structure of the automata as compared to partially robust, but not entirely. Least robust, there's a drastic alteration of the ECAD and changes are often dramatic, diffuse, and chaotic. This might eventually lead to class transition. So that comes under least robust. Now, there's a miscellaneous category as well because under that, some rules are have been categorized in that manner if the distant neighbor is introduced in the ECA. And for certain lambda, there is some alteration. But if you change the value of lambda, the alterations might not appear to be the same. So if the alterations are not consistent, we have named them under the miscellaneous category because they cannot be put in any of the four predefined categories. Moving forward, there is the consistent patterns as well. So this comes under partially robust, weakly robust, and least robust categories, where the if in the distant neighbor ECA diagram, we get some alterations that appear for any particular value of lambda, but they appear in a specific region with specific patterns that seem to repeat themselves again and again. So they come under the consistent patterns category. The results and analysis are here for class 2. So for operation and, there is completely robust that fall under all these categories. So these rules did not have any effect upon complying to the and operation. Consistent patterns, these all rules fall so that there were some alterations that were observed in all the rules under operation and, but they were not, they formed a particular pattern and they repeated that pattern over a particular period of time. Analysis under and would be that they are mostly robust throughout the operations. Operations or and zor completely robust. So under these, again, these rules, they did not have any perturbations. There was no changes in the heat map when introduced the or and zor operations for both of them, and the analysis was that they were again mostly robust. For operation NAND, so that is completely robust. The amount of rules has decreased here because NAND appears to be more sensitive to the changes that are appearing in the changed ECA, and there is a consistent pattern that you can also observe here. So the analysis for NAND was that it is least robust for class 2, and for operations NOR and XNOR. So there's a consistent pattern again observed for NOR and for XNOR for certain rules, and it is considered to be partially robust. As you can see, okay, we can move forward with this. Yeah. So you can see here that there's some particular observations of interest that we observed here. The similar initial space-time patterns for ECS 58 and 178 are upcoming except for diagonal line and ECA 58. So we can see here that there is the first diagram of 178 and there is of 58. They are exactly the same, but there's only a diagonal line appearing for ECA 58 for the same operations. Similarly, there is no effect on ECA 26 and 154. That is for AND operation. Absolutely, there are no effects that could be observed for 26 and 154. For OR and XOR, appearance of diagonals is similar for distant neighbors for 56, 26 and 154. And for NAND, there is 57 and 73 that are different from the other 5 operations. As in, 57 and 73 seem to be very unique for the other 5 operations, but for NAND, they seem to be very simple and there were no differences observed. And for ECS 26 and 58, that shows very similar patterns as compared to like in, I don't think it's here. Yeah, it's here. So if you can see the patterns, there's a comparable pattern generation between 26 and 58 for the NAND operation. And the NOR and XNOR, there is a comparable pattern generation for ECA 26 and 58 as compared to NAND here. So that can be observed here as well. And moving on to class 3, for the operation and this, there are five rules that come under the completely robust category, and there is 22 and 60 for consistent patterns. But as we identify this rule, it seems to be mostly robust. For operation NAND, there seems to be 3 rules for consistent patterns. There are no rules that are completely robust under this category. So there is 18, 19, and 122 under consistent patterns. And the analysis for this operation seems to be partially robust. For operations OR and XOR, this 60 and 150 rules seem to be completely robust for OR. And there's consistent patterns for 19, 18, 122, and 146. And this same for both OR and XOR operations. So we analyze this entire rule to be weakly robust. And operations NOR and XNOR, there is 105 and 126 for consistent patterns, and there is 19 and 18, which have the exactly same patterns for both of them. And this rule seems to be least robust as it gets more affected by the operations. Yes, sir. So we actually defined, that is an issue from mine, that we defined all these operations in the terms of R, alpha, beta, gamma, delta, so on for the logical operations. So R alpha here is OR operation. I just I did not correct the symbolization there. So that is OR operation, and R gamma would be XOR operation. Some particular observation about class 3 are that there is 18, 90, and 146 have intricate Pascal triangles. ECAD show complete robustness. As you can observe here, I think there's 18 and okay, it's going to be here. There's 18, 90. There's no 146 ruler because due to limited space. But yeah, we've observed that there is intricate Pascal's triangle that are appearing here for 18 and 90. And the ECA 22 and 60 have slightly less intricate Pascal's triangle, and the distant ECA shows slight changes and consistent patterns as well. This can be again observed here in this diagram, that ECA 22 seem to be more robust towards the operation, and ECA 126 has thicker Pascal triangles, ECA D is heavily diffused. So basically the distant neighbor for 126 seems to be heavily. Moving forward, these are also observations for NAND. Now, what seems to be of most interest here is there are attractor configurations emerging for rule 35, rule 30 and 45. So for few arbitrary initial configurations and delta, ECA D for 30 and 45 follow the chaotic to attractor configurations under AND, OR, and NOR, and NAND and NOR operations. And due to this reason, ECA 30 falls under the miscellaneous category because we cannot identify any pattern emerging from rule 30 under any circumstances for any operation. The results and analysis for class 4 is there is completely robust under 110 and 106 for and consistent patterns for 110 under AND operation and 41 rule 41 for AND and NAND. And similarly, the entire analysis for AND operation is that it's mostly robust. For operations XOR, NOR, and XNOR, there are absolutely no results or pattern that could be identified for the class 4 rules for completely robust and consistent patterns. So we could identify similar patterns emerging in under XOR, NOR, and XNOR operations, and that happens for rule 110. Similarly, analysis under this rule is mostly robust. So the class 4 observations are that for a few arbitrary configurations and delta, ECAD shows abrupt transitions that we can observe here as well. As you can see in the first diagram, the ECA seems to be normal, but in the second diagram, there are a lot of abrupt transitions when you introduce a distant neighbor here. This is run for 1700 time steps because initially we could not identify in a small duration of time, but then we found a lot of abrupt transitions here. And ECAD is similar to 60 and 150, and this OR yields complete robustness through class 4 and shows consistent patterns. Similarly, XOR, NOR, and XNOR produce neither complete robustness nor nor consistent patterns here. So for conclusion, we would like to say that there are 6 logical operations that we have predefined here, and OR and AND show maximum robustness. Negations, NAND, NOR, and XNOR show the least robustness. NAND appears to be the most sensitive one as it triggers more information and data changes throughout the cellular automata once the distant neighbor is introduced. And operations OR and NAND more likely exhibit complete robustness and consistent patterns respectively, and is equally likely to show both complete robustness as consistent patterns throughout all the classes. Only ECA 18 among all class 3 ECAs shows consistent pattern across all configurations under NAND, and attractor transition and abrupt complex transitions are observed here as well. The final analysis of our research was that there was no class transition that was observed. So there is a future research we can explore theoretical basis on the perturbations in the ECAs due to the interaction of distant neighbors further for complex systems as well. But this is what we've done till now, and this is only like we have only scratched the surface of distant neighbor interactions for ECAs. So I would like to end this by thanking Sukanta sir and Biplav sir for their inexplicable contribution and support and guidance throughout the research work, and the Indian Summer School of Cellular Automata for helping us go through this research work as well. Thank you so much.
Thank you, Swasti. Is there any question?
Hello.
Yes, sir.
And this is very nice talk. I want to know one specific comment. I mean, the statement that have you observed the changes between class 3 to class 2 or vice versa?
That is what we said, that there are no class transitions observed. That is the issue, that we thought that there might be some class transitions. There were some close to class transitions in class 3 and class, so in rule 30 and rule 45, but they were not exactly class transitions. So there were no class transition from class 2 or class to class 3 or class 3 to class 4 particularly.
Even not in class 4 to class 3?
No.
Strange. Okay.
No, sir.
Other point, you have taken periodic boundary condition, right?
Sorry, sir?
Boundary
Yes, sir,
condition
yes,
is
sir, yes, sir.
periodic.
Yes,
You
sir.
have not tried with null boundary condition.
No, sir.
Right. And what is the distance here you have taken? Distant neighbor. What is the
Yes,
distance?
sir. So we have taken it in multiples of 5 and 2. So it's 5, 10, 15, 20, and it's like 2, 4, 8, 16, and all those till the n minus 1 lattice size. So basically.
Okay. And it is one-way interaction. You are saying one-way interaction. What if you allow two-way interaction? Have you tried?
So actually, we restricted ourselves because the simulations are very lengthy. So we had to limit ourselves to some areas so that we can focus on that particular area. But yeah, that is the future scope of investigation in this particular research area.
Yeah. Another point, just you have talked about robustness, partially robust. Yeah, that is specially basically based on the space-time diagram only, right?
Yes, sir. Space-time diagram and heat maps that we've observed through
one.
that.
Another way may be regarding their cyclic behavior, reversible and irreversible. That
Yes, sir.
behavior, based on that, whether you are getting robust, this robustness you are getting or not, that might be. You can
Definitely,
export
sir.
that
That
one
is.
also. Okay, good.
I did not completely understand. Do you, from every cell, you have a distant neighbor, or only from one cell?
Sorry, sir. As in, for every cell, as in, no. We have defined one particular cell, that is cell A, and we have taken a distance lambda from that cell, which is going to be predefined. So we have taken only that cell, and that is going to affect all its neighbors from there on. So that is the one cell which is being affected by a distant neighbor, that is cell B, and it's a one-way interaction between both of them through logical operations.
My question is, do you have 4 neighbors for every cell, or do you have 4 neighbors for only one cell?
No, only one cell. Only one
only
cell.
one cell.
Yes, sir.
Okay, and okay, no, I understand better. Okay, thank you.
Thank you, ma'am.
Next, I would like to call Arijit Ghosh. His topic of discussion is tracking rule revolution in 2D cellular automata, analyzing state changes and image transformation dynamics.
Good afternoon, everybody. I am Arijit Ghosh, a research scholar at Institute of Mathematics and Applications, Bhubaneswar, presenting our paper entitled Tracking Rule Evolution in Two-Dimensional Cellular Automata, Analyzing State Changes and Image Transformation Dynamics. The outline of my presentation. The introduction to my paper, cellular automata are influential models in image processing, capturing complexity of patterns and structure in digital imagery. In CA, tracking examines evolution of individual pixels, which focuses at micro-level transformations. Our work is a type of image processing and not only generating multiple copies of images of pixels, rather to track the evolution of 2D CA. The formula computed in our paper for tracking of pixel formation not only works for the XOR operator and states in Z2, but works for all operators, multiple states, and other binary operations. In previous paper, extensive work has been done in 2D CA, especially in the replication and multiple image formation. However, in this present paper, we have focused on the denseness, sparseness, and overlapping property of images. What we wanted is how a pixel is moving in the 2D grid. That means the trajectory of a pixel. Also, fixing a position, what all cell values passes through my present pixel. So this paper investigates the dynamics of state changes and visual transformation within two-dimensional cellular automata. The fundamental rules and derived rules. By Moore's neighborhood, we understand the state of a cell is influenced by the cell's current state and the state of the 8 neighboring cells. Now, telling something about the fundamental rules and their movement, rule 232, 8, and 120, they display left shift, right shift, upward shift, and downward shift. However, considering the diagonal rules, that is the rule 4, 16, 64, and 256, they display distinct behavior. Applying rule 4 to a rectangular grid of order R cross C, it has been seen that the pixel traverses every element of the matrix requiring RC iterations. On the other hand, if we take the square matrix, the iterations reduces to R only. Now the derived rule, a derived rule is formed by the combination of more than one fundamental rule. Taking for example rule 15, so it is formed by the combination of 4 fundamental rules, 1, 2, 4, and 8. There are 512 rules possible using this Moore's neighborhood concept. The whole 512 rules can be grouped into 9 categories based on the number of fundamental rules involved in a given rule. We have used the periodic boundary condition for the generation of the images. Explaining the concept by taking an example about the derived rule, what we have done is we have taken the rule 6. We have taken rule 6, which is made up of 2 fundamental rules, rule 2 and rule 4, applied on a single active pixel and have generated the images for 8 generations. What we observe is that our aim was to track the formation of the cells. How we did that? We considered one pixel initial active cell at a point, say 5,5. What we have done, we have applied rule 6 over there. Now rule 6 is made up of 2 fundamental rules, rule 2 and 4. It is due to this rule 2 that one image will be formed at position 5,4, and due to rule 4, one image will be formed at position 4,4. Again applying rule 6 in this second generation, we got due to rule 2 an image has formed at position 5,3, and due to rule 4 another image has formed at 4,3. Similarly, from 4,4 we will get 2 images or 2 values being formed at the respective pixels 4,3 and 3,3. However, in this generation we observe that though we have 4 values obtained, but at one particular pixel 4,3 there happens to be overlapping of 2 values. It is due to the property of the XOR operator by which the value becomes 0 at that particular position. Hence, in this particular generation, that is generation 2, we are getting only 2 active pixels. Proceeding likewise by the help of this traversal tree, where the pixels denote the nodes and the height or the levels that denote the generations, we will be able to know the formation of images, how many pixels are formed at each generation, how many pixels are formed at each generation, where the pixels will be formed. The fundamental rules basically shows the directional flow of the values of the pixels. This table shows the positional values on the application of a fundamental rule. What will happen? Explaining this concept, suppose now I actually come to my work. Suppose I am at a position x, y. which pixels value has come to update in my present position is can be calculated from the formula written in this table. For example, rule 2, the formula is x comma y plus n. That means suppose I am at position 5 comma 5, which pixels value has come to update in my present position? The answer is of course 5 comma 6. So relating this concept, we have found certain formulas which we are showing for the fundamental rules, that is the group 1 rules in this table. All of us know that a group 2 rule is made up of 2 fundamental rules. Now, how to track the formation of image? From the previous table, we will calculate the, we will get the positional value coordinates for the respective fundamental rules. We will then we will collect the corresponding x coordinates from x coordinates, and from this positional value table of group 2, we will get the positional value of x, like that, x plus z and so on. Similarly, we will be able to get the positional value of y. Explaining this concept, so this is the pixel prediction formula, the general pixel prediction formula that we have given in our paper. Here x comma y is our present position, n is the n number of generations, g is a number ranging from 0 to n, and the summation symbol is denotes the XOR operator, and that modulo operation is taken because of the periodic boundary condition. R and C denotes the number of rows and number of columns. Explaining this concept by taking an example, consider a rule 12. Rule 12 is made up of the fundamental rule 8 and fundamental rule 4. From the fundamental rule table, we will obtain the coordinate x plus n comma y for rule 8, and we will also get the for rule 4 we'll also get that value. Now what I have done is that I have collected the two x coordinates, and from the group 2 table, the positional value for the x coordinate I got is, that is x plus n. Similarly, I will get for y, put in the pixel prediction formula, and will get to know whether an image will be formed at a particular pixel at particular generation or not. Again, explaining this concept, suppose I take an initial configuration, an active pixel, suppose say at the position 10 comma 10 in my first generation, whether an image will be formed and what are the pixels responsible for it. By fundamental rule 8, the pixel 11 comma 10 is responsible, and due to that rule 4, the pixel 11 comma 11. Hence, by this small calculation, we have come to know whether in the first generation, what are the pixels responsible for the formation of an image at a particular pixel. Here 10 comma 10 for first generation. Proceeding likewise, we will be able to know whether image will be formed at a particular generation, say generation 4, for a particular pixel. Not only this, from this pixel prediction formula, we will be able to know what are the distinct pixels responsible for the formation of an image at a particular position. Not only this, we also see the coefficients that also appear in the pixel prediction formula. The coefficients that appear in the pixel prediction formula obeys Pascal triangle rule. It is due to the specific operator, that is the XOR operator, by which the even coefficient terms they become 0. Thereby only the odd coefficient terms are reflected in the output image matrix. By the help of this pixel prediction formula, we will be able to know directly, without computing the intermediate generation steps, directly at the nth generation, whether an image will be formed at a particular pixel or not. What are the pixels responsible for the formation of an image? The pixels responsible for the formation of an image is done or is tracked by the help of this by the backtracking method. So here we show the level-based recursion tree for backtracking for fourth generation we have shown over here for rule 12. Those are the base case cells responsible for the formation of an image. It's very much simple and clear that the nodes, they denote the pixels, and the height or the levels of the tree, they denote the generation. One more thing also we observe over here, how the values in a particular pixel, they get transformed to various pixels. That is how the transfer of the pixels happen over here. This I have already told. Since our quest is not only confined to the XOR operator, so here I show the images being generated for various operators and using different rules, like we have used the operator AND, OR, NAND, NOR, like this. What happens over here on the left hand side, we have used the XOR operator and have taken the rule 340. Rule number 340 is a group 4 rule. As such, we will be getting 4 images at respective generations. What we observe over here is that images are formed in like this manner. What happens at generations of 2 to the power k, there happens multiple copies formation. However, sometimes the multiple copies, they overlap to one single pixel, due to which we get the these type of images. It is due to the overlapping that the images are dispersed like this. Since our formula works for all operators, all states, and different binary operations, so we have taken the OR operator over here and have seen how the pixels are being formed, how they are distributed, how they are dense in nature, and just not appear in like this manner. So here I just want to say, from among so many things, so the cardinality of the pixels can be calculated by simple formula: number of active pixels in the initial matrix multiplied by number of pixels formed by a groups rule. Though the cardinality is determined, but their positions will differ. One particular thing also I want to note, that at positions of 2 to the power k, it has been observed that the number of pixels in the output matrix is same as the number of pixels in the input matrix. So this type of behavior happens due to the superimpose of the values at particular pixels. This type of behavior is an unpredictable behavior, or rather we can say disadvantage, that we are not sure whether to get distinct number of pixels at the 2 to the power k generations. As generation increases, the distance between the pixels also increases. So we can also say that applied rule determines the number of copies formed, and the generation count influences the distance between the pixels. Here we have generated the various images using different rules, different operators, and for different generations. Till now, we have been using the uniform rules to generate the images. However, images can also be generated by the use of non-uniform rules too. The non-uniform rules can be applied by the following 4 ways: by applying rules from different groups in the same generation, by applying different rules of the same group in the same generation, switching to different group rules across generations, and following a completely random sequence of rules for each generation. We have applied the condition 3 in our experiment. We also say the total number of pixels formed in the non-uniform rules is given by R1, R2 up to RP. What is this R1, R2, RP? R1 is a rule from group R1. R1 is the group number, R2 is the group number. We have applied a rule. So explaining the concept, we have to a single active pixel, we have applied rule 6 up to generation 4, and then rule 54 up to generation 8, then rule 3 up to generation 8, and then again rule 32 up to generation 8. So the number of pixels formed can be calculated as 6 is a group 2 rule, 54 is a group 4 rule, 3 is again a group 2 rule, then 32 is again group 1 rule. So multiplying, so we will get 2 multiplied by 4 multiplied by 2 multiplied by 1, so total 16 pixels. Similarly, we can use different non-uniform rule sequence to generate various images. So the goal is to generate more copies in varied pixel positions. Suppose I want 50 pixels from one single active pixel. How to do so? So by carefully choosing the rule sequence, so we can choose a group 2 rule and 2 group 5 rules, which we can do from a choice of like 5,71,536 rules. So statistically, this says the distribution of pixels within the matrix. We have seen the like number of pixels formed at generations of 2 to the power k. While doing the experiment, we also saw pixels being formed at generations other than 2 to the power k. Consider the generation number 30. Expressing it in exponential form of 2, we can express like those 4 terms: 2 to the power 4, 2 cube, 2 square, 2 1, those 4 terms. We claim this the general formula in our paper. We also say maximum active pixels formed can be calculated by the formula p to the power q. P is the number of fundamental rules and q is that number of terms in the generation sum. I explain this concept by taking an example. To a single active pixel, we have applied a group 3 rule, say rule 7 I have applied, and wanted to know the cardinality of pixels formed at generation 2. So how? So what is the cardinality of the pixels? So simple calculation is rule 7 belongs to a group 3 rule, and that generation number 2 consists of only one term. So 3 to the power 1 only 3 pixels. Similarly, we can calculate the cardinality of pixels for different generations like 6, 14, and 30 generations. Okay, 2 minutes. Till now, we have use the fundamental rule matrix to generate the images. Now a natural question will arise: what happens if we alter the positions of the rules within table 1? With such alterations, we are left with a total of 9 factorial possible conventions. Explain the concept by taking an example. We to the fundamental rule matrix that I have already shown in the first slides. So we have just permuted, we have just rearranged the rules, and after that applied rule 30 for generation 32. Now so we got to see the number of images being formed. Since rule 30 is a group 4 rule, so surely we will get 4 images being formed at the generations of 2 to the power k. Now where are the images being formed? So due to rule 2, its image will be formed opposite to it, that is at the position of 16. So there the image will form due to rule 2. Rule 4's image will form opposite to it, that is at the position of 128, and so on. If again we rearrange the, that means if we do the permutation again, we will get the still same number of pixels due to rule 30, but their positions will differ. Here I would like to show the rule sequence with asynchronous cellular automata. How we have done this? We have done this by taking 3 parameters: the rule number, the operator, and the position of the CA at time step t. I explain only one of the spiral diagrams, that is the figure B. We have taken this as the rule sequence: 8 2 times, 2 2 times, 128 4 times, and so on. And we have applied the we have taken the position x comma y, and we have applied from position x minus 1 comma y. So this is my like the rule. I would like to say 8 to the power 2y, and so on. So this is our rule sequence. So the rule sequence is not unique. And by the application of a rule, surely we will get patterns, but these patterns are sometimes chaotic, simple, or periodic. The rule sequence applied is asynchronous in nature, but flexible too. So now, what is means what we want, like the chosen sequence determines the resulting image. Conversely, suppose if I want a desired image, then that can be done by appropriately selecting the rules. So conclusion, so what are the things we have done? Already told. What we have not done, we have kept as future work, like due to the limitation, some limitation we have, like not yet tracked for other groups. We have done only for group 2. For group 3, group 4 we will do subsequently. We will explore more about the properties of the rule sequence, and we will also explore images using different states and other binary operations too. So these are the references.
Thank you, Arijit. Any question?
Okay. It's a Arijit, good one. So when you are talking about non-uniformity, non-uniform rules,
Yes, sir.
you have used temporal application of rule, right? Temporally, you have applied different rules. And spatially, have you applied different rules? You're talking about rule sequence.
No. We have applied synchronously. We have applied everywhere.
And temporally, I mean the first one time, say first time
Yes.
one rule,
Yes,
then
sir.
after some time another rule,
Yes, sir.
and that way.
Sir, due to
Okay,
this
okay,
time,
okay, okay.
I'm not able to
Okay,
explain
got it.
but like that, we have applied.
Acha. So do you have a plan to apply them sequence? I mean the use of rule sequence.
Yes. We are working on our next. This due to the limitation of that paper pages, we have not shown there, but we are working.
Okay, that maybe then you can compare temporal application and special application of the rules, different rules. What are the difference? Result you are getting.
Thank you, Arijit.
Thank you.
For next talk, I would like to call Shauna, Despeckling images using cellular automata, elementary cellular automata.
Good afternoon, everyone. So the topic for my work today is despeckling images using elementary cellular automata. So speckle noise is a major challenge in satellite and medical images as it hides crucial details which are necessary for analysis and diagnosis. Now the question comes, what is a speckle? So speckle is a type of noise which appears as a granular noise pattern with bright and dark spots that distorts the underlying features of the image, making it difficult to read. So if we see this slide, the left image is a speckled SAR image and the right side one is the despeckled or clean SAR image. So this noise particularly affects the variance of the pixel values rather than their mean intensity because because of that it creates a textured appearance which hides the details. So various techniques have been used to denoise or despeckle these images. And talking about cellular automata, so we have 2D cellular automata which have focused on denoising images, but they have dealt with either Gaussian or salt pepper noise. And to the best of our knowledge, we have not yet seen a paper or a work discussing despeckling of images, that they have not addressed the speckle noise. So therefore, the goal of our research or this work is to despeckle images using ECA-based rules. So I'll just move on to the methodology section. This is the data acquisition part from where we are acquiring the data. Virtual SAR, this particular data set is designed for denoising algorithms. They have a set of pairs of noisy and clean images. The real side image is downloaded from NASA's Vortex website. And one more medical image we have taken, breast cancer ultrasound images. Now, I'll explain the methodology, what we are doing. First, the image, one second. First, the image, what we are doing is we are patching it. And after patching, we are assigning new pixel values to particular pixel. Suppose that, one second, I'll show it here. So if you see the grid on the left-hand side, this is a particular patch, 3x3 patch, and these are the values. So first, what we are doing, we are assigning new pixel values to this to every other pixel in this patch. How we are doing it? We are taking the mean intensity of this particular patch. In this case, it is 98. So the pixel values which are greater than 98, we are assigning it as 1. The pixel values which are less than 98, we are assigning it as -1, and which are equal to 98, we are assigning it as 0. That is the first step of our methodology. Second, after we are getting the new pixel values, we are calculating the sum of all these values, excluding the central pixel, because the central pixel is the one on which we are trying to make changes. Now, after calculating the sum, in this case it is 4, we have tested all the other rules, like all the 256 rules that are present here. So what we are doing, if the sum's value is 4, then we first convert the 4 into 3-bit binary representation. In this case, it is 100. And now, according to the rules, whatever rules we are checking, we have checked all 256 rules. So whatever rules we are checking, we are seeing the next state of that particular one binary value. So here for 100, it is 1. So now, according to this, we are trying to make changes in the central pixel. Now, how are we making those changes? It is like if the next state value, if the sum is positive, like here we calculated the sum. After that, we took the 3-bit representation of that particular value and then saw the next state. Now, if the sum is positive and the next state of the sum is 1, like just in this case, then the central pixel value is incremented by 1. So if it is 127, then it becomes 128. And if the sum is negative and the next state of the sum is 1, then the central pixel value will be decremented. And if it is the same, if it is 0, then it remains the same. This is how we have tried to accommodate this algorithm and see it together to denoise images. And if we go to the results section, this is just the overall steps what we have done. So we have tried to compare our particular model with the existing filters, and we have used different performance evaluation metrics such as PSNR, which is peak signal to noise ratio, and higher PSNR value signifies better denoising performance, as can be seen from this graph. Second is the structural similarity index measure, which checks whether the structure of the original and the denoised image are somewhat same or not. A higher value represents better preservation of structures. Next metric used here is EPI, which is Edge Preservation Index. So Edge Preservation Index basically tells us that after denoising, whether the edges have been preserved or not. So higher value indicates better performance. And another metric is a no reference metric called Perceptual Index. So it suggests the better perceptual quality. A lower value suggests better perceptual quality, meaning that the despeckled image appears more natural or visually closer to the original clean image. These are the results of various iterations performed of Rule 245. So first one is the noisy image. Second is the denoised. First is the clean, second is the noisy image. Third is after 15 iterations, what kind of image we are getting. This is after 25 iterations, and this one is after 40 iterations. Yeah. So in conclusion, I would just like to say that we have tried to introduce ECA based method for effective speckle noise reduction, and future work will focus on trying to uh, incorporate 2D CA as well as non-uniform CA for despeckling purpose. Thank you.
Thank you, Shauna, for the nice talk. Is there any question? Yeah.
Sona, please go to the first slide.
First,
First one. Yes, the second one. These two images, the first one is the SAR image, and the second one is the. Are you really sure it is a SAR image?
yes. Because it is from a data set. That is a SAR data set. It has clean and noisy images, the
And
pairs.
second one is the denoised image.
This is.
I think I have some doubt. Second one is the optical image. You can go. I mean, you can go and check.
Okay.
That one is not the SAR image. SAR image should not looks like this after denoising also.
So I guess we have.
You
I'll
just
check.
go and check.
Thank you. Yes, sir.
You have used one-dimensional CA. You tried to understand. Go to that slide. You are using one-dimensional CA. Right. So actually, I can read the sum. How you are getting the sum? Actually, if sum is positive.
Yes, sir, I'll explain. So here, after we are assigning new pixel values to the particular patch. How are we assigning the new pixel values? We are first taking the mean intensity of whatever the pixel values are there. After that, that particular intensity, the average intensity becomes our threshold. Now comparing the pixel value, that is 128, the left side one, with 98. So it is greater than 98, then we are assigning 1 to it.
Well,
if it will be less, then we'll assign -1 to it.
Okay.
And if it will be equal, we'll assign 0 to it. And we are making changes on all the other pixels other than the central one.
Sounds, yeah.
Then the sum we are calculating. After calculating the sum, we are representing this particular value 4 as 3-bit representation.
Why?
So
Sum
that
you are
we can-
taking. Okay. Wait. So you are taking a cube here.
Hmm.
You are getting sum of all cells after doing all this operation, and you are converting it 3-bit binary number, right? And then you are using some rule, ECA rule.
Yes.
What is the rationale, logic behind it of doing all these things?
Sir,
I mean, my question actually is why your ECA is here? How ECA is coming to the picture?
okay.
Any clue?
So we tried to experiment image processing and CA together.
You are taking 2D figure, 2D image. You could use, although you have said you want to do it in future.
Yes.
But generally, what do you think? You 2D is CA. I mean, sorry, 2D image. So you can use 2D CA to do some operation. But what you are doing, image is 2D, but you are using 1D CA. So mapping is needed, and you are doing this kind of mapping, right? Doing summation, etc., etc. And you are not evolving even the CA. There is no evolution of CA, rather only the rule is used, right? So I wanted to understand actually when you're talking about. So I was trying to figure out why you are doing so. Any reason is there? No, just have tried.
I've tried.
Okay. Are you getting good results?
Not that much good, but average results we are getting. Like it is able to surpass a few of the filters, not the DL methods.
Okay. Again, you find out if it is good
we'll
or
try
bad,
to-
why it is so. Without doing this using CA, if you do it arbitrarily, will you get the same result or the different result or improved result? Because it seems to me that you are taking some binary bits, representing some value, some binary, and assigning some values 0 and 1. uh, I didn't find much CA here actually. Okay, you find it out why you're getting, if you get good result, why you're getting good result. Okay.
Okay, sir.
Just one point. If you get all 1 in the neighbors, then it will be 8.
Yes,
Then how can you represent by 3 bit?
that is a limitation. We'll have to work on it.
Okay. So due to time constraint, so no question can be entertained. So during break, you can ask question to Shauna. Thank you.
Okay, now now we'll disperse for lunch.